Everyone, and welcome to topic 8. Today we are going to focus on reviewing a little bit of rules with our radicals. Now, in math, a radical is an expression that uses a root. Most commonly, we use a square root. Now, there are other roots. You could put like a cube root, like for a little 3, or a 4 would indicate a fourth root. But most commonly, we deal with a square root, which undoes a squared value. We have like a little 2 there. We just don't usually write the 2 with our most common radical. We just kind of assume this means square root. Otherwise, it would have a different root in there. Now, when it comes to breaking down a square root, sometimes we don't have perfect squares. We use a factor tree, so using factors of that to break it down as much as possible so that we are left with the value on the outside. If we can break it down and then a value on the inside that doesn't have any perfect squares associated within it. So each time we break this down, we want to move that, they move out as a pair and become 1. And then any of those other factors left over inside get simplified underneath. So notice square root of 6, we can't break that down anymore. Now, there are some numbers that are perfect squares. For instance, when we take the square root of 16, that breaks down to be 4 times 4. Right? So that's a perfect square. There's nothing left over. Right? We have a nice, pretty whole number, no decimals. Same thing with 81. That's 9 times 9. That's a perfect square. Right? The problem is if we look at, for instance, the square root of 24, that's not a perfect square, right? We have this decimal and notice these are irrational. We cannot turn them into a fraction. So this is where we would need a factor tree. Now, ideally, right, we like to look at our list of perfect squares. So this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, these perfect squares, and see if any of them are factors will make our life a little bit easier. For instance, 4 is a perfect square times 6, that equals 24. And this is nice because we know 4 is a perfect square. We have that set of 2's that would move out as a perfect square. Now 6 is just 2 times 3. That doesn't break down anymore. So 2 and 3 would stay inside the radical. So the pair of 2's move out and become a 2. And then we have 2 times 3 left over inside for a total of square root 6. Okay, again, when we move this set out, they move out as 1. 12 also can be broken down to be 4 times a value, this time 3. Again, 4 is a perfect square. That pair of 2's move out. Now, notice we already had a 4 on the outside. Now we have this pair of 2's moving out. They'll get multiplied together. And then we are left with 3 on the inside. Final answer on this one, 8 square root 3. All right, last one. We have 810, which is 81 times 10. 81 is 9 times 9, that perfect squared. 10, however, breaks down to be 5 times 2, which doesn't really help us at all. Those are not going to be able to be broken down. So we move the pair of 9's outside of the radical. 5 times 2, we would just leave that square root of 10 inside the radical. All right, now we have some for you to try on your own. -8 square root of 32 to square root of 54 and break down the square root of 400. All right, next page, we are talking about multiplying and dividing radicals. So when we multiply radicals, the numbers on the outside, for instance, 4 and 3, get multiplied together, and then the radicals on the inside get multiplied together, and we get our final answer. Now, always double check, can I break this number down on the inside? Similar to the last page, if the answer is yes, we want to make sure we do that. No, otherwise we keep it like this. Dividing, okay, again, kind of works. You would divide the outside numbers by the outside numbers. In this example, there are none, so we wouldn't worry about that. And then the inside numbers, square root of 10 divided by square root of 2, you could think about rewriting it as just 1, and we would get square root of 5. All right, so looking at some more examples with multiplication, notice what's happening on these first couple examples. 4 times 4 is 16. That's a perfect square, so we break it down to be 4. 7 times 7 is 49. Again, a perfect square. We get 7. So notice there's kind of this little rule here. Anytime you multiply a square root by itself, what ends up happening is the number under the radical is your answer. Okay, so notice on this one, square root of 4 times square root of 4 is just 4. Square root of 7 times square root of 7 is just 7. On this next one, square root of 2 times square root of 2 is just going to be 2. And then the 4 times 2 ends up being 8. Next examples, though, we're not multiplying something by itself, so we're going to have to be careful. Outside numbers get multiplied together. 2 times 6 is 12. Inside numbers get multiplied together. 5 times 3 is 15. Square root of 15 does not break down to have any perfect squares, so this just ends up being our final answer. Second one, 8 times the number 1 on the outside here is just 8, and then we end up with 10 times 2, which is 20. Now 20 we can break down to be a perfect square of 4 times 5, so we end up being able to move out a 2 as well. So we end up with 8 times that pair of 2's that move out, so that's 16. The 5, however, stayed inside. So 16 times the square root of 5. Right, try the next one on your own. We have 4 square root 2 times 2 square root 2, and 2 square root 7 times 4 square root 3. All right, now dividing, again, you want to think about if I am writing this, I'm dividing 16 square root 21 by 4 square root 3. So I can divide these numbers on the outside. 16 divided by 4 is 4. And then these numbers get divided by each other. 21 divided by 3 is 7. Can't break that down anymore, so 4 square root 7's our best answer there. Second one, again, we're going to divide by the square root of 3. Numbers are both underneath the radical. Square root of 75 divided by square root of 3 is actually the square root of 25, which is a perfect square and just ends up equaling 5. Last but not least, when we divide this by the square root of 2, these actually just end up canceling out. Anything divided by itself, including a square root. So square root of 2 divided by square root of 2 cancels out, and we're just left with 4. All right, last big thing we are going to talk about today is the idea of rationalizing. Okay, we do not like, a radical on the denominator, right? We can have a radical in the numerator, but we don't like that radical on the denominator. So again, going back to what we talked about up here, anytime you multiply a square root by itself, it just becomes that number underneath the radical. So what we do is we multiply top and bottom by the value from our denominator. So square root of 2 times square root of 2 just becomes 2. And then 8 times the square root of 2 is just 8 times the square root of 2. Divide then these numbers on the outside because they can be simplified. We end up with 4. Okay, so again, if we look at number 5, we have square root of 2 in the denominator. We don't like that. So to keep this an equivalent fraction, we're going to multiply top and bottom by that value. And then anytime you multiply a square root by itself, it's just that number underneath the radical. So just 2 on the top, 6 times the square root of 2. Last but not least, you always want to double check. Can we simplify? 6 divided by 2 is 3. And then we just leave that square root of 2. On the next example, we are given square root of 3 in the denominator. We don't like that. Square root in the denominator. So square root of 3 times square root of 3 is just 3. 18 times the square root of 3 then is our numerator. Again, double check, can we simplify this? 18 divided by 3 is 3. Keep the square root of 3. Last but not least, we have a square root of 2 again. Square root of 2 times square root of 2 is 2. 7 square root 2 in the numerator. This time when we look, can we simplify this? 7 divided by 2 cannot be simplified. So we would just leave that because 7 is not divisible by 2. We just leave it as 7 square root 2 over 2. Again, 3 examples for you to try and rationalize yourself, A, B, and C. All right, last but not least, we want to be able to solve these radicals. Okay, so something we could do here to get x by itself is divide both sides by 3. And what we notice is not only did those 3's cancel on the left, but they also canceled on the right. So we're just left with x equals square root 11. Second one, again, we want x by itself, so we're going to divide both sides by the square root of 40. Again, it cancels out on both sides, and this time we're just left with x equals 11. Now, unfortunately, on the next one, when we divide both sides by square root of 3 this time, it cancels on the left, but not on the right. So right now we have x equals 21 divided by the square root of 3. Well, this looks very similar to the bottom of this page where we need to rationalize because we don't like that square root on the denominator. So we're going to multiply top and bottom by the square root of 3. We end up with 21 square root 3 over 3. And then last but not least, 21 is divisible by 3 this time. So we're just left with 7 square root 3. Now on the next one, instead of dividing to get x by itself, notice x is in the top, square root of 2 is on the bottom. So we're going to multiply both sides by the square root of 2 to cancel that out, right? So x is by itself. We have square root of 11 times the square root of 2, which ends up just becoming the square root of 22. Can't be broken down anymore. It's not going to break down to be any factors 2 times 11. Those aren't perfect squares. Same idea then. In this one, we need to multiply both sides by the square root of 11 to cancel that out. We get x equals 8 times the square root of 5 times the square root of 11, which is the square root of 55. Again, we could double check, but 55 is not going to break down to be any perfect squares. These are not perfect squares, so this is our best answer. Last one. This time, again, we have to undo that multiplication through division. X is by itself, but unfortunately, we are dividing by a square root, right? So we have to rationalize, multiply top and bottom by the square root of 2. So 11 square root 2 over 2. 11 and 2 are not divisible, right? 11 divided by 2 is not going to be simplified. So we just leave it as 11 square root 2 over 2. All right, we have a couple examples for you to try at the end here. Try example A, B, C, D, E, and F. Any questions, let me know. Thanks for watching.